Okay, so our first topic will be sets. Okay, so this is what you will be learning in 11th class maths in the beginning. Okay, so we'll have our first lesson today. Okay, maybe we'll have our second lesson on Monday.
Okay.
Okay, so before we move on, can you guys tell me what a set is?
Something which stores numbers.
Okay, something which stores numbers. Okay, how about you, Om?
Uh, like it is something, a collection of something, sir.
Collection of something. Okay. Now, how definite is this something? Can you give me an example? Let's say an
So
example.
height in a class.
What is it, Harsha?
Heights in a class.
Okay, heights of students in a class. Okay. How about you? Om?
Alphabet,
Can I?
alphabets, numbers, some
Okay,
dates.
alphabets, numbers. Okay. What kind of numbers?
For suppose natural number, real number, integers, these all things.
Okay. 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 So all those are sets. Okay. Can you give an example of what might not be a set?
So preferences like favorites.
So why do you think?
So because
then set?
everyone's favorites cannot be same for others too. So it cannot be stored in a set.
Okay. Okay. So that means our set has to be defined very carefully, right?
Yes.
So it cannot be vague. So it has to be defined very carefully. So that is why a set is a well-defined collection of objects. Okay, so you have a collection. So we have a group of something, okay, group of objects, and they have to be well-defined. Okay, so if an object is in the set, we need to be sure that, okay, it is eligible to be in the set. Right. So if you look at the example that Harsha gave, the heights of students, yeah, for each student, you have measured his or her height, and then you are putting it in a list. Okay, so that is a set. Set of natural numbers is a set. Is zero a natural number? Guys, is
No, sir.
zero a natural number?
No, sir.
No. Okay, very good. Okay, example of sets. Let's look at few more examples. Okay, I think this Om was telling, right? The set of vowels in the English alphabet is a set. Now, okay, what are the elements in this set?
A-E-I-O-U.
A,
I-O-U.
I, O, U. How are they decided? I mean, do we have a role? Like, or somebody has decided already? We are taking it for granted that they are well defined. Okay, yeah.
Somebody has already decided it.
What is that, Om?
Somebody has already decided it that those are
Okay,
vowels.
somebody has already decided, but there is a definite criteria, right? Okay, so only these 5 letters are A, E, I, O, U. We know only these are in the set, the others are not in the set. Okay, so there is a definite criteria. Okay. So we are not debating at least for this set. Okay. But if we are defining a set for ourselves, we need to make sure that, okay, if a particular element is part of a set, it has to have a definite definition. Okay. So another example of a set. Here it is when you start talking about, let's say, sets with numbers, it becomes convenient for us. Okay, so multiples of 3 between 101 and 151. So you know numbers from 101 to 151. Okay, so if you go from one number to the other, you know whether it gets divided by 3 or not. Okay, so the division by 3 is the criteria. Okay, so if a number has to be in the set, it must be divisible by 3. If it is not divisible by 3, you don't put this in the set. Okay, so you know on what basis you are selecting an object or an element to be in the set, right? So here this words like object, element refer to what you are putting in the set. Okay, so now what you are putting in the set can vary from your context to context. Okay, so in the previous example, we said uh, you have a vowels ka set. So that will have, let's say, A, E, I, O, U. Okay, now these are the elements. Okay, so these are just the letters of English alphabet. Now, but here, can you just give me some numbers that will fall into this set? Multiples of 3 between 100. 102. Okay, so you divide 102 by 3 and then see if it is getting divided or not. Okay, if it gets divided, you will put it here. Okay, Om, can you tell me one more number here?
Next one is 105, sir.
105. Okay, so and so on. You can go. I mean, let's say, what do you think is the last number in this set?
150.
150. Right. So here I have some letters. Here I have numbers. So what this tells us is the element in a set can be anything actually. Okay, but in the beginning we will be looking at the simple examples. But you can actually, if you want to put, you can put anything, right? All it says is the set must be well defined. Okay, so you are deciding on a criteria. Okay, you would be using that criteria to decide whether to place an object in the set or not. Okay, an object passes the criteria, you will place that in the set. If it fails the criteria, you don't place in the set. Okay, so again, we are sure which numbers belong to this set. Okay, let's take another example of a set. Okay, a list of capital cities of Indian states. So can you throw in some examples?
Thiruvananthapuram.
Thiruvananthapuram. Okay, this depends on your knowledge, but yeah, I think we know few. Okay, Thiruvananthapuram. Okay.
Gangtok.
Gangtok. Okay, what else? Harsha? Bhubaneswar. Okay. So you can form a set, right? So here you have the names of cities. So, okay, Hyderabad is the capital of Telangana state. So we can say that it will be part of this list.
Yes.
Okay. Ooty is the capital of any state? Is it the capital of Tamil Nadu state? So this will not be part of the list. So what is the criteria here? We're just saying, okay, if it is the capital city of any Indian state, then it will be in the list. It will be part of the list, becomes a member of the list or an element of the list. Otherwise, it will not. Okay. Again, I'm using here, if you see the word set, the word list, the word collection. Okay, you can use, let's say, group, we can use, but I think when it comes to our class, instead of calling, let's say, as a group, a collection, or a list, you call it a set. Okay, now what is not a set? So you cannot really place, if you are not sure, okay, whether to place an object in a set or not, the definition is not very clear, then you cannot have a set. Okay, so for example, if you say you want to make a set of 5 best sweets, okay, now is this a good criteria? I mean, it's a 5 best sweets. We might feel, okay, so your you might have a preference for the best, putting let's say sweets in a category, okay, and then 5 best sweets will be there. But can you be sure?
Yes.
We can't be sure. I mean that your taste itself might change, right? Our taste might change, and when you ask, let's say, your friends, they might give a different group of 5 sweets. Each of them might give a different group of 5 sweets, right? So, for example, instead of 5 sweets, let's say we are making a set of 2 best sweets. Okay, now, Om, can you give me, let's say, 2 best sweets according to you? Whatever like come to your mind immediately.
Rasmalai
Okay, Rasmalai,
and Rasgulla, sir.
Rasgulla. Okay, Harsha, can you give
Yes.
it to whatever comes to your mind straight away? Whatever you like the most.
Halwa, sir.
Halwa, okay.
And
See, so it's very difficult to define, right? It's very difficult to define. So such things are not called sets. Okay, so if the criteria is not very clear, we say that there is no set there. Okay, so taste varies from person to person. Hence, criteria to decide the best sweets varies. So we don't have a set here. And another example. So if you say, okay, you're making a collection of 7 most beautiful Hollywood actresses. Again, this varies, right? Who is making this list? Okay, so if you are making a list, there will be a different, let's say, list of actresses' names. If I am making a list, it will be different. Okay, it really depends. Okay, if Gautam is making, he will have a different list. Okay, it really depends. So, for example, Scarlett Johansson.
sir.
You know this heroine?
Yes, sir. She
Okay.
played Black Widow.
Black Widow. Yeah. So I like this heroine, but my friend doesn't really like her. So when you actually want to have a set of 7 most beautiful actresses, it is very difficult to say which actress will become part of the set. Okay, so the criteria is not really clear here. Okay, so it varies. So we don't call, let's say, such groupings. I mean, you might, let's say, you can still call it as a group. Okay, you can call it as a collection, but it is not a set. Okay, so in maths, we are trying to define it very, very clearly. Okay, so if we can't have a clear definition, it is not a set. Okay, important sets in mathematics. Okay, so I think Om was talking about a few of these sets in the beginning, right? So he was talking about natural numbers, integers, real numbers. Any other sets that you guys recall?
Like set of positive integers.
Okay, set of positive integers. Anything else?
Real numbers.
Real numbers, we are done. Okay, there's one more thing.
Set of natural. I think we are done.
Natural
Rational numbers.
rational numbers.
Yeah,
Okay. Okay. Now you know the symbols for each of these sets, the letters that are used for each of these sets.
yes, sir.
Okay. So I think yeah. So N stands for the set of all natural numbers. You have Z, the set of all integers. If you place a plus sign, okay, above Z here, if you see, if you place a plus sign, that is a set of positive integers. Okay. And then Q stands for rational numbers. What are rational numbers, by the way? What are rational numbers, guys?
So they are fractions.
They are fractions. Okay. So if you have a number, oh, sorry, guys. So if you have a number,
It can be defined as P by Q, and where Q is not equals to, P is not equals to 0, sir.
very good. Okay, so you can define this as P by Q. And what are these P's and Q's? They are
They
any?
are natural numbers.
No, they are any integers. Okay, so they are any integers, and your Q cannot be 0. Okay, not just natural numbers. I mean, you can have a -1/3 also, or you can have a -3 also, which is like -3/1. That's also a rational number. Okay, so your P and Q, they are integers. Whatever you have in the denominator, that cannot be 0. Okay, that is the criteria. R is the set of all real numbers. If you again place that plus sign there, you have set of positive real numbers. Okay. Now, this is understandable, right? Whatever objects that you have inside this set, you can call them as members or elements. But I think mostly we will be using this word elements. Okay. So elements of the set, I think it is more preferred compared to objects or members generally. And then, okay, so whenever you are trying to define a set, usually capital letters are used to denote a set. Like we had like N, R, Q. Okay, and then, but I think in mathematics, if you see those R's, N's, they're actually special symbols actually. So if you really look at R, you might have seen it is not just written as R. Okay, so you have that double line and then you write it as R.
Yes.
But you don't have to do that. If you just write this way, that is also okay, and it's understandable. But whenever you have a set, you usually use capital letters. It's not necessary, but usually you use capital letters to denote a set. And for the elements in the set, you can actually use small letters to denote them. Okay. Now, this usually happens when you have elements, but you don't know what those elements are. Okay, so you are keeping them as a variable, unknowns. Okay, so then you can use letters. Okay, so do you know any methods that are used to represent sets, which you learned in earlier classes?
There are two methods, sir. One is tabular form,
Okay,
also known as
roster form. Okay,
and another is set builder form.
very good. Okay, so very nice. So you have a roster or a tabular form. The other one is a set builder form. Okay, so these are the two methods to represent a set. Okay, so let's look at each of them. Okay, now roster form with some examples. So what do we do here? All elements are separated by commas, and then you place them inside. They're enclosed by braces. Okay. So, for example, the set of vowels in the English alphabet. Okay, so you have these braces here. Okay, so you have these braces, and all the elements of the set are enclosed by the braces, and they're separated by commas. Okay, this is what you do in the roster form. Okay. Then another example, set of what happened quickly. Guys, just a minute. I think Okay. 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 So if you look at the other set of prime numbers, sorry, prime factors of 154. So only these are the numbers which are prime and divisors of 154. Okay. So you place them in between braces and then separated by commas. Okay. So this is the roster form, basically a list or a table. Okay. This is, you can call it as a tabular form also. Then, okay, now this is important, guys. So in roster form, the order of listed elements has no importance. Okay, so there is nothing like an order. Okay, so when you actually list the elements in a set, you might usually put them in order. Okay, so like in the previous example, if you look at the vowels, you will always place as they appear in the English alphabet. Okay, so A comes before E, but you don't have to. Okay, so you can actually mix them up. Okay, so there is no need to maintain the order. Okay, so similarly, the other example, the prime factors, I can place 7 before 2. Okay, it's still the same set. So understand that the order has no importance. Okay, so the following roster forms represent the set of odd natural numbers less than 10. They're all identical. Okay, so all these sets are actually identical. So if you look at them closely, in the 3 representations, you have the same elements. Okay, and I think even if you repeat one element, it doesn't affect. Okay, it will still be the same set. I think both the order and the repetition, usually we don't repeat, but order and repetition has no importance. Okay, so just keep that in mind.
Okay.
Okay, now Greek symbols. Okay, so we will have to look at a couple of Greek symbols that are used in understanding sets. Okay, so this is, you call this epsilon. Okay, so this is epsilon. And you read this as, whenever you look at this, you read it as belongs to. Okay, and there's another symbol. Okay, so you have that epsilon and then you put that slash across this epsilon. It's called epsilon naught. Okay, now whenever you see this, you read it as does not belong to. Okay, so these symbols are used to, let's say, write in short notation to indicate whether an element belongs to a set or not. Okay, so that's the purpose. See, what you really need to understand is maths is a language, right? Okay, so the more we try to understand maths, I think it's important to treat it as a language. Okay, so you're trying to learn a new language. So then there's a lot of language elements that you need to understand, and the new language elements have to be learned. Okay, so there's a lot of symbols and their meanings have to be learned as you go along. Okay. So let's take this set. Okay, so if you have a set of natural numbers less than 20 that are either divisible by 2 or 3, so you have this set. So now, if you take 12, 12 is part of the set, right? 12 is part of the set. So you can write 12 belongs to A. Okay. Now, if you take 7, 7 is not really part of the set. So you say 7 does not belong to A. Okay, so how do you read this? 12 belongs to A and 7 does not belong to A. So the symbols give you some meaning, right? Okay, so they're convenient. I mean, if you know what they stand for, they're really convenient. Okay, so they allow you to express what you want to say without writing too much. You understand? So this is what you generally do when you actually write proofs. Okay, when you write proofs, instead of using like English words to write, okay, 7 does not belong to A, you just write 7 epsilon not A. It is very convenient. You get the point.
Yes, sir.
So set builder form. Now, what is the set builder form? Any idea? You recall what a set builder form is?
Instead of using actual elements, we are writing a sentence where it's
Okay, so when you say you're writing a sentence, what exactly is that sentence? How is that sentence used? What is the sentence
Uh,
used for?
we are taking a variable for suppose x, y, or z, and
Mhm.
then we use a colon over there. So then further, um, for suppose, for example, sir, x, there is a set of natural numbers till 5, sir. So we can write x colon x is
Okay,
x
let me
is
read.
1 equals to, or
X is
x is uh, greater than, greater than or equals to 1,
okay, so X is greater than or equal to 1 or
or less than or equal to 5, sir.
5. Okay, so what is basically you're writing here? You're just mentioning a condition, right?
Yes.
So there's a condition which each of the elements in the set, let's say, follow. Okay, so you can say that they kind of condition or a criteria that is expressed. So here you're not really listing the elements explicitly. Okay, you're not listing them out. You're showing a criteria or a property shared by each of the elements. Okay, so that is why it is called set builder form. Okay, so you're building a set. Okay. So common property shared by all elements is used to represent a set. Hmm? Now, sets of natural numbers less than 10 and divisible by 3. Okay, so this symbol means 3 divides. If you look at this, so from here to here, this is your property shared by the elements of the set. Okay, so this is the property. So you're writing, this is the property. Now, but again, this is actually little vague if you think about this. No? I need to fix this. How can I fix this? This is not very, it's okay, but I think it's not really, what do you say, completely correct. Okay, so if you, what is the problem here? If I'm saying I have a set of natural numbers less than 10 and divisible by 3. So in this, I have a property, okay, which is shared by all these elements,
Okay.
but I'm not really happy with the way I have defined. Can you fix this? So this symbol means 3 divides x. So this means 3 divides x. Suppose x is, let's say, 6. X is 6. Will it be part of this set? Yes, right?
Yeah.
Okay. Now suppose x is minus 6. Will it be part of this set? Okay.
Yes, sir. It would be.
It would be, right?
Yes.
It would be, right? So how will I fix? Because I'm saying I wrote here set of natural numbers, but the property that I have is actually allowing me a number minus 6 also to be part of the set, which is not a natural number. So how do I fix my condition or the property that I have put here?
You can take positive numbers.
Exactly. So either I can actually change the condition here. I can say that, okay, X lies between 0 and 10, or I can leave it as it is, but I can add, okay, I can add, let's say X belongs to natural numbers. I can do that. You guys understand? Then I would have kept a property which is correct. Okay, so I think in roster form, sometimes you use dots. Why do you think dots are used?
To show whether the set is finite or infinite, sir.
Very good. So whether the set is finite or infinite. So if you, in a finite set, is there a place for dots?
No, sir.
Why not? How do you know? Let's say the set of first 100 natural numbers. Can I use dots to represent the roster form?
No, sir.
Why not? Let's say, why can't I do something like this? Is this a finite set or an infinite set?
Finite.
It's finite, sir.
It's a finite set. Okay, so here, I think you can use it for both finite and infinite set. It depends. I mean, mostly it is used for infinite sets, but if you have a list which is very big, okay, so you can have your dots in between also. You get the point? Okay, so dots are used to indicate numbers that exist indefinitely, but there is an identifiable pattern. Okay, so here you have some numbers. I maybe like this indefinitely. This is usually okay for a infinite set, but not for a finite set. So I think here you need to understand that this is just a limited one. Okay, so numbers that exist indefinitely, but with a pattern. Okay, you have to have a pattern. If there is no pattern, I don't think you're going to place them in a roster form. You understand this? So if you have a list of numbers without a pattern, you don't really place them in the roster form. Okay. So set of squares of natural numbers. Okay, so there is a pattern here, right? So 1 is the square of 1. Okay, so 4 is square of 2. 9 is square of 3, and so on. Okay, so here these dots indicate that you have many more numbers to follow. Okay, now how do you read this set builder form? Okay, I think this is again, you know something. I think most of the sets that is there in your 11th class, I think you might have already done in your lower classes. Maybe when did you learn sets? 10th or 9th? 9th class? No? You didn't have sets in 10th?
No, sir.
You had?
No.
No? Oh, okay. I thought you had. Okay. Okay. So I think let's quickly look at this. So this curly braces, okay, so curly braces, you read it as the set of, okay, set of all X. This is like such that, and then you have the property. Okay, so common property connecting all elements. Okay. Okay, so let's take an example. Okay, now, okay, before I discuss, can you just take a minute to write down, do this simple exercise? Write down the set of all one-digit prime numbers in roster form. Okay, so let's verify. Okay, so do you have these 4 numbers?
Yes, sir.
Okay.
Yes, sir.
Okay, so do you have any Any numbers more than this or fewer than
No.
this? No, right? Okay, good.
No.
Okay. So try this one. So what are the elements in the list?
Sir, 2 and 3.
2 and 3. Very good. Okay. So Om, you agree?
Yes, sir.
Okay. So these are like simple things that you have learned in 10th class. Okay. Okay, so let's move on. Let's take another example. Okay. So now try this one. These things will take practice. Okay. You have seen in one of the previous examples that even I was not, what do you say, entirely correct in expressing it in set builder form. Okay. So these things will take time. Okay. So this is how you should write. So in set builder form, we are saying you are having a property, right? So x is an integer and x square is less than 9. So you can use this. But now when x square is less than 9, integers means you should immediately think that even negative numbers are allowed, right?
Yes, sir.
Okay, so if you look at it, x square is less than 9. Okay, so if x square is less than 9, first just imagine square of what number is 9? 3.
Yes,
Right?
sir.
So that means you are really looking at numbers which are less than 3. But again, the moment you pay attention to integer, you know that negative numbers can also be part of this list. So then you can go till -3. Okay, so but you are really looking at less than 9. So I cannot include -3 and 3. So any number between -3 and 3. When I say any number, any integer between -3 and 3 will be part of this list. Okay, so these are the numbers. We are okay with this? Okay, now this is like if I give you something like this, x square less than 9, it is very easy to do. But slowly you might have to do slightly complex problems wherein the inequality, this is called an inequality. The inequalities can be complex. So in that case, we will have to learn methods. Okay, so those methods, I think I'll teach you. Yes, slowly. But even here, if you think, you can actually write something like this. So x square, this 9 can be brought to the left-hand side. -9 is less than 0. Now you have something in the form of a square minus b square, right? X square minus 3 square. So that is less than 0. Now this you can write it as x minus 3 into x plus 3 less than 0. Now you have two factors. You're multiplying them, and then you should get less than 0. So what do you mean by less than 0? You're multiplying two numbers, and then you should have a negative number. When is that possible?
What, sir?
When both are positive, it is not possible. When both are negative, it is not possible. You guys understand? One of them has to be positive, the other one has to be negative, right? You understand? Okay, so what generally is done is you identify something known as a critical point. Like you see, instead of less than 0 or greater than 0, when is this really equal to 0 first? When is this equal to 0? When x is 3 and our x is -3, this becomes 0, right? So you take your number line, you point, let's say, put those on the number line. Okay, so you have -3 here and 3 here. So if you take any number beyond -3 to the right, you know that x plus 3 will be positive and x minus 3 will be positive, right? You're taking, for example, you take a number 5. You take a number 5 what will happen? 5 plus 3, 8, that is positive. 5 minus 3, 2, that is positive. Okay, so positive into positive, you will not get a negative number. Okay, it will not be less than 0. So that means this is not going to give you a solution set. Okay, that means this is not going to give you an answer. But if you move to, let's say, this region, what will happen? For example, you take a number. Okay, so convenient example is 0, let's say. You take 0. So if you take 0, this 0 is greater than minus 3. So that means x minus 3 will become what? X minus 3 will become negative, but x plus 3 will become positive. Negative into positive, it will be negative. So that means your solutions lie in this region. Okay, and then again, if you go here, both will be negative. So then this again will not going to give you any answers. Okay, so such a method is known as a wave peak curve method. Okay, so it's kind of, it looks like a wave. Things change. I mean, things change in the sense they go from, sorry. What is happening? Just give me a minute, please. Where did I write? I think it made it. So I lost it anyway. So whatever I wrote a little earlier, it's a method that you use to solve inequalities. Okay, so we just started, right? So don't worry too much about that. When you learn something known as how to solve inequalities, you will learn a lot of methods. Okay. 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 Do you guys want to try this? No? Okay. Yeah. Right. Okay. So let's verify. So do you guys have all these?
Yes, sir.
Okay. Very good. Hopefully you did not place 8 there.
No.
No, right? Okay.
No.
So let's say, okay, now, okay, I'll give you one more minute to work on this. Okay, so look at this. So we're saying x, you're using another variable, which is n cube, let's say. What is n? N belongs to natural number. See, the moment you say n belongs to natural number, you know n is an infinite set, right? N is an infinite set. 1, 2, 3, 4, 5, and so on. So your small n is used to represent each of these elements in the natural number set. And then we are saying, okay, you're going to cube them and then get the elements in your set. You're okay? So let's see how you defined. Okay, so Harsha, how did you define this?
Sir, I just wrote x is equals to n cube.
But if you say x is equal to n cube, what is that? Capital N did you use? Or small n did you use? You cannot use capital N because it gives a different meaning, right? I mean, you are like cubing the set, which is not allowed. Okay. So remember, we wrote earlier, the small letters are used to represent elements in a set.
Yes.
Okay. So you cannot use capital letters, notations wise. Okay. Notations wise, we have to be careful. So it's not that you have to use only small n. You can use y also. You can say instead of n, I can use y cube, but y belongs to natural number. Okay, so the moment you say that here small n belongs to capital N, you are saying that n takes place of each of those natural numbers. Okay. But if you only say n cube, you have to mention what your n is, right? You understand, Harsha? You have to mention what your n is. Om, how did you define this?
Sir, I wrote it like x is such that X cube is greater than n, and
But
n is a natural number, like that.
okay, but again, you said x cube is greater than small n or capital N.
I actually wrote a capital N, sir. That's all.
But does it have any meaning here?
No, sir.
Because you are on one side you have some number, on the other side you have a set. You cannot compare a number with a set. You understand?
Yes, sir.
So here you're trying to bring in another variable. Okay, so you read this as set of all x such that x is, you are taking the cube of some other variable now. But what that variable is, it is used to represent each of the elements in the natural number set. You guys are okay here?
Yes.
Okay, so let's try one more. Okay, now this time try your best. Okay, let's hear from Harsha. Harsha, tell me.
The x is n by n square plus 1.
Okay, x is,
N by n square plus 1.
okay, so you're writing Q as, let's say, set of all x such that x is,
N by n square plus 1.
n is n by n square plus 1. Okay,
And n belongs to natural number.
n belongs to natural numbers.
And n and 0. And n is greater than 0 and less than 6.
Okay, very good. So n is greater than 0 and less than 6. Okay, I think, yeah, this looks okay. So you wrote exactly like this?
Yes, sir.
Okay, very good. So, Om, you understand? I think this should be okay because I think it captures all these 5 elements.
Yes, sir.
I think you are saying that you got this pattern, right?
Yeah.
Okay, so let's see. So it's almost the same, but what I wrote here is instead of x in between 0 and 6, I included. Okay, so instead of
Equals.
using less than, I use less than or equal to.
Yeah.
It means the same thing. Very good. Okay, so now let's look at a few more types of sets. Like there is a null set or a void set. Null and void mean the same thing. So what do they mean? What comes to your mind here?
They are empty.
Empty. Okay, so that means there is no element in that set. Can you give an example of an empty set? Okay, suppose in your school, no student is allowed to attend classes both in 11th class and 12th class, suppose. It's usually not allowed, right? So if it is not allowed, then if you are saying, okay, I have a list of students who's attending both 11th class and 12th class, then will you get any students in that list? You will not get any students in that list. So that's an example of an empty set, or you can just call it a null set or a void set. Because a set which does not contain any element. Okay, so that's a null set. Okay, again, we have a Greek symbol here, which is important. So you have to remember this symbol. Okay, so you know what this is? This is P. Pi T, I think it's generally called P. It is used to denote the empty set. Okay, guys, it is like those capital letters. Earlier we were using capital letters to denote certain sets with elements in them. So here it is like those capital letters, but it is a special symbol. Okay, I understand the epsilon naught, they are used to indicate whether there is a membership or not, whether an element is in the set or not. But here this symbol is used to denote a set. Okay, so basically this actually means if you are writing in the roster form, you have curly braces, but you have nothing inside. Okay, there is nothing. Nothing inside. You're getting? So that's the empty set. Okay, so finite set, I think the word finite itself is telling you what this is. Okay, now question. Is an empty set considered a finite set? You understand my question? Is an empty set considered a finite set? Okay, so here you need to be careful. Is an empty set considered a finite set? An empty set has no elements in it.
No, sir.
Can I consider it as a finite set?
No.
Yes, no.
No,
What
sir.
do you think?
I guess yes, sir.
Yes. So by definition, you consider it as a finite set. I mean, I don't have anything in that. So it's technically finite because there are zero elements in that, right? So having no elements gives some definiteness to it, right? So you can consider an empty set a finite set. That's how you understand. It looks, yeah, it might feel a little uncomfortable, but that's still considered finite. Okay, so a set which is empty or consists of a definite number of elements. Okay, so you can have elements, but if there are no elements also, it's a finite set. Example, okay, so the days of the week, this is a finite set. You know how many elements are there here. Okay, so what elements are there? Okay. So Sunday, Monday, and okay, what is an infinite set?
Natural numbers.
Natural numbers is an infinite set. Okay, so like you have many numbers. So set of those elements cannot be counted. Okay, so for example, you don't know what that is, right? Some large number with a negative sign, it becomes a very small number. Okay, and then you have 0, 1, 2, 3, and so on. It's an infinite. Okay, now again, few more symbols case. These are important. You have to understand this. These two mean the same thing, guys. Whatever new symbols we are learning, you try to revise them on a regular basis so that you get used to them as early as possible. Okay. So here S is a set. We are using N of S, or you're placing these vertical bars. Okay, so that mean the same thing. What this really means is number of distinct elements of a non-empty finite set. Okay, so you have a non-empty finite set S. Okay, so if you write N of S, it is telling you how many elements are there in that non-finite set. Sorry, non-empty. What am I saying? Non-finite, non-empty finite set. And then you place that vertical bars. This is called cardinality. Okay, so cardinality, this is also known as a cardinality of a set. Cardinality is like you're just trying to figure out how many elements are there in a set. Cardinality of a set.
Those bars are also used in modulus, I think.
Yeah, those bars are also used in modulus. See, these bars are used in several places. In modulus, you are trying to, let's say, if you, it depends what you place inside the modulus. Okay, so whenever you see these bars, so here you can have a set, you can have a simple number. Later on, you will learn something known as complex numbers. You can have a complex number. You will learn something known as vectors. You can have a vector. Okay, so you can have many things inside. Okay, so but I think in most of these cases, you are getting a number out of it. You're getting a number of it. Suppose if you have -5, what is this telling you? It is telling you what is the distance of -5 from the origin. How far is -5 from the origin? Then you would say it is only 5, right? So you're getting a positive number out of it. So if you take +5 also, you're getting the same thing. Okay. So when you place those vertical bars and when you have numbers in between, the meaning is you're getting the absolute value, but how do you read it? You can read it as like, what is the distance of -5 from the origin? -5 and 5 are at the same distance from the origin, so they have the same answer. Okay, but here when you place a set inside, the meaning is different. Here you are counting the number of elements. You understand now? The meaning is different here. Here you are counting the number of elements. Okay. So suppose you have this set of vowels in the English alphabet. So the number of elements is 5. Okay, or the cardinality is 5. So you can also write this way. Okay, so if you place that vertical bars, that is also okay. So you can use this as well. You're okay with this? Any questions here, Harsha? Questions? Okay. Okay, now look at this statement. Roster form cannot be used to represent set of real numbers. Okay, so real numbers are like many, right? Can you put them in a roster form? You cannot, because when you put in a roster form, you need to have some pattern, some sort of pattern, right? But real numbers, there are many, so you cannot really place them in a roster form. Keep this in mind.
Is it possible in that set builder?
Set builder form, yes. Real numbers, you can use set builder form. Okay, set builder form is okay because you are defining a property, right? So you can define a property and then place. But when you are using a roster form, you have to list the numbers. Suppose if you have a set builder form, let's say I try to say that X says that X belongs to real numbers, and if I say the X is between 1 and 5, suppose. Now this is valid, right? I know what are the possible values of X. Okay, so any number between 1 and 5 is okay, any real number. But how many real numbers are there between 1 and 5? Guys, how many real numbers are there?
3, sir.
Infinite.
Infinite, not 3. Harsha, we are looking at real numbers.
So it includes rational and
It includes rational, it includes irrational. Okay. Now, you might have studied in lower classes that if you take any two rational numbers, there are infinitely many rational numbers between them. There could be irrational numbers also. So you cannot really put them in a roster form. You understand? Because there are infinitely many numbers. Okay. So, and if you put some of them numbers, how will you judge what other numbers will be present, right? You understand? So even though the set builder form is giving you a definite idea of what numbers are in the set, but you cannot take the help of a roster form to represent the set of real numbers. You guys are okay?
Yes.
Okay. Okay, equal sets. Now, when you say A and B are equal, what do they mean? They have exactly the same elements. Okay. So A has the same elements, B also have. B, whatever elements which are there in B, they're also there in A. That's the idea. Okay. If A and B are equal sets, then we use A equal to B. Now, again, guys, you have to understand here, this is having a different meaning. You guys understand? Let's say, if you say, let's say X, Y, if they belong to natural numbers, and then if you say X is equal to Y, you're comparing the values of X and Y, right? You understand here? But here, when this equal to sign is operating on the sets. Okay, so you're using the same symbol, but it is having a different operation. For example, if I define A as a set of, let's say, the first 4 natural numbers. Okay. Now, I can also say, let's say B is X such that X minus 1 into X minus 2 into x minus 3 into x minus 4 equal to 0. That's a weird way of defining my set. Okay. Now, this is a slightly complicated equation than your quadratic equations that you know. But if you solve them, you'll get x is equal to 1, 2, 3, 4, right? You guys understand? And you put x is equal to 1, this is 0, 2, 0, 3, 0, 4, 0. Okay. So here you can say that both these sets will have the same 4 elements. So you can say A is equal to B. So on either side of equality, you have sets here. Here you have numbers. And if they don't have the same elements, then what do? You use not equal to. Clear here?
Yes.
Okay. Now, this is again important. A set does not change if one or more elements of the set are repeated. Okay. So, for example, I have a set 1, 2, and I have a set 1, 2, 2, 1. Both are equal. Just because I have repeated 2 and 1, it doesn't become a different set. These two sets are equal. So if I call this as A, this as B, in this case, A is equal to B. You get the point? Okay. Yeah. So, however, it is a bad idea to repeat any elements. Okay, so we don't really generally repeat while describing a set. Okay, so if you are using roster form to represent a set, you don't really repeat the elements. Okay, subset. You have any idea of a subset, or by looking at the word, does it tell you something?
In a set, sir.
What is that?
Like in a set, there is another set, sir, inside.
Very good. Okay, so a set contains another set. Very nice. Okay. So from the important sets in mathematics, can you give an example? Like a set contained in another set.
Like a whole number. Whole number contains natural number also.
Very good. Okay, so if I use a circle to represent, let's say this circle represents whole numbers, let's say W. And then I can have another circle, say this circle represents natural numbers. Okay, so the set of natural numbers is contained in the set of whole numbers. So you can say N is the subset of W. Very good. Harsha, you are saying something. Sorry, I couldn't.
Like in integers, positive integers and negative integers.
Very good. Okay, so in integers, if you divide the integers into positive and negative integers, yeah, the positive integers is subset of all the integers. Negative integers also. Very good. So here, yeah, a set is said to be a subset. Set A is said to be a subset of set B if every element of A is an element of B. Okay, very good. Okay, now symbols. Again, few more symbols here. If A is a subset, how do you write? You use this, I don't know, what is a sleeping U? You can say sleeping. Kind of sleeping U, okay? So use this symbol to indicate subsets, okay? And then otherwise, you use this, okay? So A is not subset of B, okay? Okay, again, yahan par let's pay attention here, okay? So very closely. If A is a subset of B, what does it mean? Every element of A is in B, right? But now how about B? Every element of B may or may not be in A. You guys get the point? Okay, so there may not be any elements in B left over once you count all the elements in A, but there may be certain additional elements. So for example, let's say I take Z plus. Okay, so Z plus is what? It is
positive integers.
Positive integers. So positive integers means 1, 2, 3, and so on, right? But if you take natural numbers, also the same thing, right? So here, If I say that N is a subset of Z plus, I can also say Z plus is a subset of N, right? In either case, let's say when I say N is subset of Z plus, in Z plus, I don't have any extra elements left. But if I have whole numbers, suppose, whole numbers, I have that 0. So here, if I say N is subset of whole numbers, I have this 0 which is left out. Okay, which is not present in the set of natural. So you guys understand? Harsha, you're okay here?
Yes.
So there may be elements in B, there may not be elements in B which are not in A. No, okay. Okay, now this can also happen, right? If A is subset of B and B is subset of A, what does that mean? They are equal sets. This symbol means implies. Okay, so if and only if they are equal. No, sorry, this is not implies. This means if and only if. Okay. So if A is subset of B and B is subset of A, imply if and only what this statement means is you can actually come from right side to left side or left side to right side also. If A is equal to B, if you have two sides and then say A equal to B, that means they have exactly the same elements, right? So in that case, you can say A is contained in B, B is also contained in A. A is subset of B and B is subset of A. Okay, now can I say this? Every set A is a subset of itself. Guys, can I say? You can say this, okay? Okay, this again is important. Do you guys agree with this? Phi is a subset of every set.
But it doesn't have any like blank empty set, right?
Exactly. Okay, so here we have to be very careful here. See, I know. Okay, so phi does not have any elements in it. Okay, but it is considered. Okay, it is considered a subset of every set. Okay, now how do you understand this? So either you can take it by definition. Let's say, see, phi is an empty set. Suppose I have the natural numbers. Okay, I know I have some elements here. Okay, I have some elements here. Now, in this case, if you are trying to form subsets, let's say, using natural numbers, suppose, for example, if you're forming subsets using natural numbers, how would you do that? Let's say you're forming a subset A by taking some of the natural numbers.
From 1 to 10.
1 to 10, right? So you say 1 to till 10. Okay. But I might say that here, when you formed a set 1 to 10, that means you left out the numbers from 11 and onwards. Okay, so you did not pick them, right? Now it can also happen that you don't select any number. It is possible.
But how does it make a subset?
I did not select. See, I did not select any of them. Okay, I did not select any of them, right? See, suppose, let me take another example. If a room is inside another room, that room can be empty.
Yes, sir.
Okay, so there are people in that room. And then that room is inside another room. In that room also there are people. Okay, so technically that room is inside that bigger room with people.
So A is a subset of B set, you say?
No, you cannot say A is subset of B, na? See, it's like maybe that room analogy. Let's take that room analogy. So if I have a bigger room, okay, so there are few people inside that bigger room. And then there is another smaller room. There may be few people in that room, or maybe that is empty. Can I say that that room is contained in the bigger room? You can say that.
Yes, sir.
So similarly, you have such a definition here. Okay. So I know I have a set which is a null set. You can treat it a part of every set. Okay. Maybe you can take it by definition. Okay. You're getting?
Yes.
Yeah. So this is something that you have to keep in mind. This is important actually. This is very, very important. Okay. So there are certain statements like that. Okay. So there are certain statements like that. But I think that room analogy should help you remember this. Okay. So a room can be inside another room. That room can be empty. So that's still contained in that. Okay. But there you are able to see a room. Here you are not able to see a null set. But by definition, you can take a null set as a subset of every set. Okay, Harsha?
Yes, sir.
Yeah. Okay, so let's take. Okay, so you try this. You're saying this is true?
Yes, sir. It is.
Yes, sir.
Yes. Okay. So what are the? Can you just let's list the elements in set A. What are those?
2, 3, 5, 6.
2, 3, 5. Okay. So how about B? That's
2, 3, 4, 5, 6.
okay. So you already have the elements which are there in.
Can we include 1 also?
Very good. You can include 1 also here. Okay. So the moment you just say devices, even 1 can be there. Okay. So yes, the answer is yes. Okay. Now again, proper set and superset. Okay. So these are again. Now, what do you mean by proper subset?
Sorted.
What is it, Harsha?
Sorted the.
No, it's not about sorting.
Yeah.
See, remember we said A is a subset of A, no?
Yeah, sir. Yes.
So that means they're equal sets, but when you say A is subset of B, in B, you don't have to have additional elements which are not present in A, right? So when A is subset of B, B may have elements which are not present in A, or maybe B does not have extra elements at all. Okay. In that case, in either case, you are calling it a subset. But when you say proper subset, B will definitely have additional elements. Will have extra elements. You guys understand this? Then you say A is a proper subset of B. And then B will be called a superset of A in that case. In that case, you say B is a superset. So if A is subset of B, then A is not equal to B. Then A is called proper subset of B, and then B is called the superset of A. You guys understand this?
Yes.
For example, let's say if I take natural numbers and whole numbers. Now I can say that the natural numbers is a proper subset of whole numbers. And then if I take the whole numbers, I can say it is a superset of natural numbers. Get the idea? Just because of that extra element 0. Okay. Okay. A set with just one element is called a singleton set. Okay. So just let's say definition. So keep this in mind. So what is a singleton set? A set with just one element. Okay, so I will let you answer. Okay, so let's think about it. The first thing, they're saying A belongs to B. Okay, A belongs to B. That means what? If I take, let's say, B as a set, suppose B as a set, I might have some elements, but I must have A inside B. You understand? A is a set which is inside set B. Now I might have some other, let's say, for example, I can take A as just a singleton set. Let's say A contains only one, number 1. Okay, now B can be A, 2, 3. So my B is a different set. Okay, so my B is having 2, 3, but also an element which is a set. This is allowed. You guys getting? Are you with me so far?
Yes, sir.
Arsha, you
Yeah.
understand?
Yes, sir.
Okay, now let's look at this. The way they have said is B is a subset of C. Now, if B is subset of C, there are two possibilities now. Okay. Now, if B is subset of C, I can write, I must have all these elements in C. You guys understand? Okay, so let's say 2, 3, and let's say 4. Then, now, can I see a possibility where, in this case, if I take this one, then does it mean to say A is subset of C? Or does it mean is A subset of C? Think closely. Is A subset of C? See, if A is subset of C, what does it mean? See, here B is subset of C. What does it mean? B is subset of C. Now this is my C. What does it mean? If you take an element in B, let's say a set itself, set containing 1 itself, it is in C, right? 2, it is in C. 3, it is in C. So B is subset of C. That is okay, valid. Now, but if you say A is subset of C, what does A contain? A contain this number 1. Is 1 present in C?
Yes, sir.
Where do you see 1? See, a set containing 1 is there, but is 1 an element of C? You have to be very careful here. This is not considered. This is not same as, suppose I have another definition for C. I have 1, 2, 3, 4. Okay, so this is, I'm defining 1 explicitly here. Now here 1 is an element of C. In this 1 is not an element of C. You guys understand? This is an element. The set itself is an element, but 1 is not an element here. Are you getting the difference? Here 1 is an element. So in this case, I can say A is subset of C. But in this case, I cannot say A is subset of C. I cannot say. You guys get the difference? Arsha,
Yes, sir.
what happened? You're beating your head? You understand the difference here?
Yes, sir. I do.
So it need not be actually. You get the point.
Sir, I do.
Now, you can, this example is telling you that inside a set, you can have sets. Inside that set, you can have sets. You can do whatever you want. Okay. You get the point. Your element can be anything, not just numbers. Okay. Okay, so it need not be. The answer is need not be. Okay. I think this example should tell you why. Om, you get the point?
Yes, sir.
Okay. Harsha, okay. Any questions here?
No, sir.
No? Okay. Okay. Intervals as subsets of R. Okay. So intervals is again a very important topic. Okay. So we know that we cannot use roster form. So instead of roster form, we have an interval notation when it comes to representing real numbers. Okay. So here A, B, they belong to real number line, and then we are assuming that A is less than B. So we have these four things that you need to understand. Okay. So pay very close attention here. We take the help of this brackets, different types of brackets. This normal bracket, and then this is the square bracket. Okay, so they have a different meaning actually. So when you have a normal bracket, it actually means X such that X is between A and B, but not includes A and B. Okay, so if you have a picture in the number line, you have open circles. Open circles indicate that you're not including A and B, but everything else between, okay, every other number between A and B is contained in this set. Is everyone okay? So this is called an open interval from A to B. But if you have a square bracket, that means you're including A and B and also all the numbers between A and B. Okay, so these are very, very important set notations, interval notations. You work with them a lot. Okay, so when you actually solve problems in inequalities, in let's say using modulus function, logarithms, okay, so see, sets is the beginning. Okay, so you use sets to understand a very important topic called relations and functions next. So when you study relations and functions, you will have to understand certain things known as domains and ranges. Okay, so when you get a domains and range, there you will regularly use this interval notation. Okay, so understanding this interval notation is very, very important. It's kind of one of the foundations that you need to have. So when you use square brackets, it has this meaning per set. So you're including both A and B. So on the number line as a diagram, you have this closed filled circles. Okay, so that means you're including A and B and all the other numbers between A and B. And then here, if left side is square bracket, the other is normal bracket. That means the left side number is included, the right is not included. This is again an open interval from A to B, including A but excluding B. Again, you see the diagram here. And then left side is normal, the right side is a square bracket. So you're including B, okay, not including A. Okay, are we okay here?
Yes.
Then in each of these cases, if you take the distance between B and A, B minus A, it is called the length of these intervals. Okay, so you just call this length. Okay, so okay, I'll give you some time to think about this. How do you represent this? Any idea? Have you ever seen such things? Okay, so again, so interval notation, this is how you write. Okay, so if you see the set of non-negative integers, non-negative means 0 and positive. Okay, so your interval notation using those brackets, 0 is included, so you put 0. Infinity is just a feeling. Okay, so if you have infinity without a negative sign, that means a very large number. So you cannot really include it. So you put that. Negative again. So 0 is not included. Minus infinity is also not included. So that is. And then all real numbers, you come from negative infinity to plus infinity. So these are very, very important interval sets. So keep this in mind. Okay, power set. Okay, so now what is a power set? Okay, so let's understand this. The set of all subsets of a set A is called the power set of A. Okay, you guys understand the set. If you have a set A, it has some elements, right? Including a null set. Remember, a null set is part of every set.
Yes, sir.
Okay. So the set of all subsets of A is called the power set of A. So let's take a symbol here. So you use this P of A to indicate a power set. This means a power set. Okay, I think let's discuss this example. Okay. So you have set 1, 2, 3. So we are trying to write the power set. Okay, power set is a set. Okay, which is formed using subsets of the given set. So we need to write the power set in roster form and also find how many elements are there. Okay, so now let's look at this. So can I say the null set is also a set? I mean, null set is an element, no? So I can just form a null set, right? Okay, so that is allowed. Then I can have, let's say, just one. I can have two. Okay, I'm just taking one element. Okay, so I can have three. How many sets are done here? All these are subsets of A. Can I say? Empty set is a subset of A. This set containing one is a subset, containing two subset, containing three. Now I can have a subset like this, or I can have a subset like this. This is also a subset of A. You guys understand? And I can have this is subset, and then I can also have 1, 2, 3. Now you take all these sets as elements and then put them in a bigger set. You guys understand? Take all these subsets, treat them as elements, put them in a bigger set. That is the power set of A. Okay. So this is the power set. You guys get the point? Your null set and then this set, all sets are placed. So how many elements are there here? There are 8 elements. Get the point? Okay. So now you can think of it this way. Let's say, how do you get how many elements are there in a power set? Okay. A very simple counting that you can do is, in this example, you have 3 elements, right, in A, set A. Now, if you are making a set, okay, if you are making a set, you can include one or you can exclude one, right? In how many ways can you form a set using element 1? In 2 ways, right? You can either include it or you don't include it. Similarly, you can either include it and then you don't include it. Include it or don't include it, okay? So there are 2 ways here, 2 ways here, 2 ways here. So you multiply them. So you get 8 ways in constructing a subset. Okay. So your power set will have 8 elements. Are you getting this point?
Yes, sir.
So if A is a set with n elements in it, okay. So this remember this absolute vertical bars. It tells you how many elements are within a set. Then the number of elements in the power set will be 2 to the power n. Okay. Then universal set. What is a universal set? It is a basic set that contains all the sets in a given context. Okay, so we will see like examples later. So it is denoted by U. Okay.